Hello. In this chapter, I'm going to cover thermodynamics. We are going to discuss some concepts like energy, work, entropy, enthalpy, free energy. We will talk about the spontaneity of chemical reactions and, of course, chemical equilibrium. But again, let's start with few lessons from Einstein. What about this? I have a couple of good ones where Einstein was talking about the imagination. He said, imagination is everything. It is the preview of life's coming attractions. Imagination is more important than knowledge. What about this one? Make mistakes. A person who never made a mistake never try anything new. Something to think about. All right, so let's start with our chapter. We label it as chapter 18, thermodynamics, and we are going to cover entropy, free energy, and equilibrium. What is entropy? What is thermodynamics? What is free energy? So let's start with a definition of thermodynamics. Thermodynamics is a branch of physics that has to deal with heat, work, temperature, and the relationships with energy, radiation, and properties of matter. We're going to apply these concepts to better understand the behavior of chemical processes, because at the end, we have to study the relationship between matter and energy. Chemistry focuses more on transformations of matter. Physics is more focused on energy transformations. However, we all know that energy and matter are linked. One depends on the other. We are going to discuss application of physical chemistry and the thermodynamic laws to understand the chemical processes. This is one example of application of thermodynamics. This is a simple machine. It's called the Carnot heat engine, Carnot cycle. Where I'm trying to here update my pen, put it to work. Let me see if I can make it work. Yes, okay. I'm just testing it. All right. So on this Carnot heat engine, we have a machine that takes in heat and releases a byproduct there. So basically explains the energy transfer, heat transfer, or thermal transfer between two objects. This object here has higher temperature than this object. So the heat occurs from high temperature to lower temperature. Higher kinetic energy to lower kinetic energy. So we have a gradient there. So we are going to analyze that type of processes. So we have here potential energy over time. Natural processes likes to go from high potential energy to lower potential energy. And the systems becomes more stable because they have less potential energy. In this case, we have higher temperature and lower temperature, and this machine helps to do that. During that transition, it produces work done by the system. One of the applications of this concept is what we call the reverse Carnot heat engine. And you very well know that the application is the fridge or your AC, home AC units or your car AC units. In that case, your AC unit uses molecules that can absorb the heat, but in order to do that, you need to apply work. That's why it's called also the reverse Carnot heat engine, because you need to put work into the system. And what is that? What do you need to do so your AC unit or your fridge works? You need to plug it right into the power outlet, energy. So you need to give energy. The AC has a pump that compresses the gas, these molecules. And then they expand, they gain energy, they absorb energy from here, and then it cools down your room because it takes energy from your room to cool down. So that's one application of thermodynamics. We're going to apply thermodynamic laws. We're going to make emphasis on the first three thermodynamic laws. And that will help us to make predictions in regards of the chemical reaction, if the chemical reaction is going to happen or the chemical reaction is not going to happen. If the chemical reaction is spontaneous or not. Or what conditions we need to put into the system so the reaction becomes spontaneous or not. Also, we are going to apply these concepts to see the relationships between energy and equilibrium. And we are going to find different ways to calculate the equilibrium constant for a chemical reaction. Also, we are going to take into consideration the kinetics of the reaction and compare to those of thermodynamic conditions for a reaction to be spontaneous. So we're talking about spontaneity and non-spontaneous reaction. The first law of thermodynamics, it says the internal energy may be transferred as heat or work, but cannot be created or destroyed. Energy transforms into heat or work. And we can define that as the internal energy delta E, which is the change of internal energy of the system, equals the change of energy, the transformation. Final energy minus initial energy. And that transformation can be defined as heat and work. So we can say that internal energy of the system can be transferred as a heat and work. And we're going to play with these two principles here, these two variables. Heat, which is Q, lowercase, and work, lowercase w. And we're going to use some notation, which is called the sign notation. And we are going to follow that sign notation every time we are writing our chemical reactions. So that is called the sign notation. In other words, we use signs plus or minus to describe the direction of the process. If Q, heat, is bigger than 0, that means Q is positive. That means heat is absorbed by the system. In general, a positive sign for a variable means the system is being affected by that variable, by surroundings. If, in this case, heat is less than 0, negative sign, that means heat is released by the system. So in general, the negative sign for a variable, that means the system is affecting surroundings. Another example is work. When work is positive, that means surroundings are doing work on the system. When work is negative, less than 0, That means the work is done by the system on surroundings. So it's important to take that sign notation. Also, we assign those signs. You as an observer needs to see how is the heat flowing. What is the direction of flow of that heat or work? So you have your system here. Remember, the system, your system can be a beaker. You choose the borders of your system. You say, okay, I'm going to study this system, and this system is a beaker with a solution, aqueous solution. So you decide the limits of your system, and then you observe the direction of the process. If your system is producing heat and the heat transfer from the system to surroundings, that means you have a negative heat. And you assign, you say, okay, this heat is negative Q. If the system is receiving heat from surroundings, in other words, surroundings are giving heat to the system, look the direction. Now it's from surrounding into the system. So you say, okay, the heat is positive. So you must learn first what is the direction of the process, and then based on that, you give the sign, positive, negative. Or if during the mathematical procedure you find that the Q is positive, so you know the flow of heat goes from surrounding into the system, for example. Also, we need to recognize, to identify some state functions, like internal energy. Here, internal energy of the system, that's the total energy in the system. Your system has the energy, that's what we call the internal energy. And the internal energy is a state function. That means that the value of that function doesn't depend on how you achieve the state. So, for example, to go from point A to point B, so you will find the energy between these 2 points is called delta E, which is energy of B on state B or position B minus initial, which is energy on state A. And that change of energy does not depend on how you achieve that position or that state. You can go directly from A to B, or you want to go from A to C and then B. Delta E for that process is the same, from A to B. One of application of this concept is when you did the calculations for enthalpies of reactions, and you apply down Hess's law. Because, and that's possible because enthalpy is another state function. All right, there are two types of work. So we said that energy can be transferred as heat and work. There are two types of work that can be produced here from that energy. One is the electrical work. We're going to cover that in the next chapter, chapter 19, electrochemistry. And the second type of work is what we call the PV work. And I think I mentioned it before when I gave you this example of this machine. Using this machine, you remember the name of this machine? What was the name of this machine, this simple machine here? A piston. So what happened with the machine? We apply the machine when we have gases. If your reaction, chemical reaction is producing a gas, then that gas can do work. Work is energy, right? Heat is energy. So we have two energies here that can be due to the transformation of internal energy. You have a gas with volume 1, and then you apply it here, a force. You compress the gas to volume 2. We have here delta V of the gas. So you compress. For that, you apply work on the system. Since you are doing work on the system, that work is positive. But spontaneously, what is the normal situation? When you have a gas and you put the temperature, what is the tendency of the gas? Once you generate the gas in a piston, the tendency for the gas, natural tendency for the gas is to expand, to gain more freedom, increasing here collisions, having an average kinetic energy, which is the temperature. So the natural tendency is to go from B2 to B1, causing an expansion of the gas. And as a result, the piston goes out. In that case, the energy will be negative. I mean, the work is negative for the expansion of the gas. expansion of the gas. So we can say that the work in this case is called negative work, because talking about the natural process, which is an expansion, equals P delta V. And that is what we call PV work. And that PV work is negative for a expansion of a gas. And we can transform this definition of energy equals Q minus P delta V. But what happens if we don't have a piston? We have something like the calorimeter, something that is called the bomb calorimeter. In the case of the pump calorimeter, all walls of calorimeter are fixed. It's not, in this case, one of the walls is moving up and down. For the pump calorimeter, everything is fixed, all walls. So you have the gas here, and there is no way to produce expansion or compression. Your chemical reaction is happening here. All the heat is transferred, is water, what we have here in a pump calorimeter. All the heat is absorbed by the water. And what happened delta V? So since walls are fixed, delta V is 0. There's no change on volume here. So this expression becomes 0. That means all the energy is transferred as a heat. And that's what we say, the heat measured at constant value, like on a pump calorimeter. On the other side, if we measure the heat at constant pressure, then we have Q sub P, which is heat measured at constant pressure. And that is what we call enthalpy. The enthalpy of the reaction is the heat measured at constant pressure, and that is done on a coffee cup calorimeter. The coffee cup calorimeter on the coffee cup. Okay, I'm traveling here. Okay, here. In the coffee cup calorimeter, we have a system that we try to be as much isolated as possible. We said the coffee cup because coffee cup is made of styrofoam, which is some kind of isolation. In the lab, we use the coffee cup to run chemical reactions, but they are open to atmospheric pressure. And that's why we say it's a constant pressure, because in the lab, the atmospheric pressure is more or less constant. And the heat transferred here is measured as delta H. That will be heat measured at constant pressure. So in general, we can say that the internal energy of the system minus the enthalpy equals negative work, negative P delta V. And this is especially valid when the reaction is producing gases, because then we have an expansion or pressure change in the system. And if we apply ideal gas laws and plug into the previous equation, we arrive to this equation here. Delta H, or enthalpy, equals internal energy delta E plus delta N gas RT. Again, delta N of gas is the change on stoichiometric number of moles of gases in the chemical reaction. For example, if we had the reaction N2 gas plus H2 gas to form NH3 gas. So delta N of gas for that reaction will be moles of gas in the products minus moles of gas in the reactives. So number of moles produced, the stoichiometric number of moles is 2 minus 4. We take the absolute value of that, and that's 2. We're going to study spontaneous changes. So what is a spontaneous change? It's a change that occurs by itself without any external help. So we're going to use those thermodynamic concepts to identify the spontaneity of the chemical reaction, to make predictions of whether or not the reaction is going to occur under certain thermodynamic conditions. A spontaneous reaction does not necessarily mean an instantaneous reaction. So let's not get confused with the word instantaneous. Some reactions are instantaneous, they occur very fast, and that has to be more with kinetics. This concept has to be with kinetics. Like, for example, the firework is very fast. That is the result of a very fast chemical reaction, which is an oxidation of certain metals and metal oxides in the presence of oxygen. So they are very fast reactions. Fast reactions. And you can say those are instantaneous reactions. Once the oxidation process gains the right amount of kinetic energy and achieves the energy of activation, the reaction goes to completion, which is a combustion. For example, iron, solid, oxidation state 0, plus oxygen, gas, to form iron 3 oxide. So we balance it there. This is a solid. Plus energy. And that reaction is very fast. But also is spontaneous for that case. But sometimes we have the same reaction because we have given conditions of oxygen, temperature. But in other situation, when you change the thermodynamic conditions, temperature, energy, the same reaction can become very slow, very. The same reaction. And the same reaction and the different condition that goes slow is called rusting, which is the oxidation of iron. So you can achieve these two processes in different ways. Like, for example, you burn dust, iron, so you increase the surface area. That reaction is fast, and you provide enough kinetic energy, that reaction is going to be fast. So a high temperature. However, the same reaction, and you put a big chunk piece of iron, or you leave your bicycle outside under the weather, and the oxygen is the oxygen in the air at room temperature, this reaction goes really, really slow. But still is spontaneous. You don't have to do anything for the reaction to go. The reaction will go all the way for oxidation. It's going to form the same oxide, or probably a mixture of two oxides. That's why the result of that sometimes is written as Fe3O4, because that is a mixture between these two. Iron, this is iron 3 oxide, whereas this is iron to oxide, and you have a mixture here of both. So you see, spontaneous reaction does not necessarily mean an instantaneous reaction. This is a combustion. Combustion is a spontaneous reaction and also is fast reaction. But there's a gradient there. Why the reaction wants to go? This is exothermic, right? If the reaction is releasing heat, so you say delta H of that reaction is negative. That means the reaction is exothermic. We are using the sign notation. Minus, that means the system is producing heat on surroundings, increasing the temperature of surroundings. And that heat or energy comes in different forms. Sound, the very loud process, light, different frequencies of light, kinetic energy of particles traveling very fast. So there are different transformations there of energy coming out of the chemical process. Here are the sources for the pictures I took. Also, I have another example of gradient for natural process, for a spontaneous process. But this in this time is, I'll show you like for physical process. I like this. The waterfall. It's a natural process, natural tendency. What is the tendency here for the water? To go from high altitude to lower altitude. High altitude means high potential energy. In this case, is gravitational potential energy. Mass times height times gravity. And you can measure the energy, the potential energy for the process. So it's a natural tendency, and that's what we call the gradient, the difference, in this case, of altitude, and the water goes from high to low. Have you ever seen naturally water going up? No, right? It's non-spontaneous. The reverse process, reverse to this, is when the water goes up. So the reverse process is non-spontaneous. This process from high to low altitude is spontaneous. The reverse is non-spontaneous. Can you bring the water up? Yes. How? Since this is not going water up, is non-spontaneous, you need to put energy into the system. So I like that to represent the physical gradient for a physical spontaneous process. For our chemical processes, we're going to identify the variables that govern these spontaneous processes and how can we make predictions about that. I mentioned it before, the entropy. No, I didn't. I mentioned enthalpy. Now, we're talking about the second law of thermodynamics. So the first law of thermodynamics talks about the change of energy. Energy cannot be created, cannot be destroyed. Energy changes from one form into another. For our chemical processes, the total energy of the system transforms into heat and work. When we have gases involved in our chemical reactions, that energy can be transformed into PV work for the expansion of a gas. So the gas can be used to produce work on the system. Also, we can measure the heat of that process in two ways, two different ways, at constant volume, or we can measure the heat at constant pressure, and that's what we call the enthalpy. Now, the second law talks about entropy. Entropy is a very complex concept. I can give you a hint about that by saying that entropy is a measure of the randomness or state of disorder of a system. We use the entropy we use the symbol capital S as a way to measure the state of disorder of a system. And that's the second law. So the second law says that the total entropy of the universe increases or is increasing. Entropy is also a state function. So we can measure final states and initial states of the system. We can measure the change of the entropy on the system. So we have a gradient, final minus initial. Final states minus initial states. This is important because that can give us a chance to take measurements in a chemical reaction. One difference from enthalpy, so we have now two functions here. Enthalpy, that is related with the heat, and entropy, that is related with the state of disorder, randomness. Now we are going to talk about the freedom of the system. Also, for enthalpy, one characteristic of enthalpy is that there are no absolute values for enthalpy for any compound or any substance. The only way to know the energy of the system is by measuring final and initial state. So we have to use as a reference the change. Whereas for entropy, we do know some absolute values of entropy for a substance. So on a data table, you can find values of entropy. Whereas in a data table, you won't find absolute values of enthalpy for any substance. What you will find is the change of enthalpy for a process. Sign notation also applies for entropy. Positive entropy means that the final state or products are more probably to happen or to occur than the initial states. So nature loves or likes, as we can see, positive changes of entropy. What about enthalpy? What does nature loves? What does nature like? What does nature prefer? Positive enthalpies of negative enthalpies. What is your answer? What is your educated guess? I can give you a hint. And I've been giving you this hint for a while because I know we were coming to this point. For that, I need to draw something that I mentioned before, potential energy diagram. Potential energy against time. So we're talking about chemical species having this potential energy here, that's the initial state. And after the chemical reaction, the products of that reaction will have this level of potential energy. And we call this what kind of process? Exothermic. Delta H is negative. And the difference of energies from initial and final state is what we call delta H, or the reaction. Here, up to here. Right there. The difference of energy between the final, which is here, and the initial, which is here, or was there. So yes, nature prefers exothermic processes. Why? Because the products gains more stability because they have less potential energy. If something has high potential energy, the tendency is to go down to a lower potential energy, similar with the waterfall. Remember? Higher gravitational potential energy to lower gravitational potential energy. So that, take this is an important hint. You need to remember to make predictions about spontaneity of chemical reactions. So most chemical reactions spontaneously are exothermic reactions. I'm not saying that endothermic reactions will not happen. They happen, but at the expense of entropy. Nature knows how to make deals in terms of energy and entropy to keep everything in balance, in apparent balance, because at the end, nothing is at equilibrium. Everything is trying to get an equilibrium. The equilibrium is being disturbed, and try to reach a new equilibrium. That's what keeps universe moving as a whole thing, as a whole system. So on our macroscopic level, we see that exothermic reactions are more probable to occur. And also increase on entropy is favored, more disorder. And this is a natural process. You can spend whole day over the weekend on Sunday cleaning and organizing your room. And you make it neat and clean, everything well organized, sparkly. During the week, you go to work, you go to study, or we used to before COVID-19. And what happened at the end of the week? Everything is in a state of disorder again. It's a mess. So it's like a natural tendency that applies to all systems, including us. So what do we need to do in order to bring it back to a normal state of order? You have to put energy, your own energy, to bring it back to order. And that cycle will happen again and again. And again and again. The system will try to stay at the maximum state of disorder. Let me show you how to measure entropies on a chemical reaction. Since we just learned that we can measure the change of enthalpy and the change of entropy which is delta H and delta S. And we say that the change is measured as final state minus initial state. So that's the concept of change or gradient. So we can apply that for the change of entropy. But let me remind you what we did before for enthalpy. So the change for a reaction A plus B forming C and D, delta H for the reaction will be the enthalpy of products, the change of enthalpy of products minus the change of enthalpy of reactants, final minus initial. So here are the products, and here are the reactives. So a more decent definition of delta H of the reaction will be, what is delta H of products? Is the sum of N delta H standard of formation of products minus the sum of N delta H standard of formation of reactives. So this is your great equation to measure or to find, to calculate delta H of reaction. And that's the definition of change, final minus initial. And we can use the same definition to calculate the change of entropies for any reaction. Therefore, delta S of the reaction equals the sum of N delta S standard of products minus the sum of delta of N delta S standard of reactives. When we're talking about standard, what is that? Standard TD, thermodynamic conditions. So somebody in any lab around the world was using these conditions to take measurements, experimental measurements, and report those measurements in a data table. So what are these conditions? The standard thermodynamic temperature, which is the absolute temperature, capital T, is 25 degrees Celsius, which is 298 Kelvin. 298.15 to be more precise, but we can round that off to 298 Kelvin. Notice that this standard thermodynamic temperature is different from the standard temperature for ideal gases. For ideal gases, we use a standard temperature as 0 degrees Celsius. And for standard thermodynamic conditions, the temperature is 298 Kelvin. As a general rule, when you are working with energies, you must work with the standard thermodynamic temperature, 298 Kelvin. What is the standard pressure? The standard pressure is the same. 1 atmosphere, 101 times 10 to the 5 pascals to the 5th. Pascals. So the concentration, standard concentration, standard molar concentration is 1 molar when we are working with solutions. So those are the standard thermodynamic conditions, standard TD conditions for thermodynamics. conditions. So again, that means all these are standard enthalpies and entropies. And how do you find these standard enthalpies of formation or standards entropies? They are listed on a standard thermodynamic data table. Let me show you the shape of that. I posted on Blackboard, so you should go to the Blackboard, download it, and print it out and have it next to you for your examinations. So you will not lose time trying to find these values in your textbook or on your papers. You need to have it next to you. Let me show you. This one. This is one version of that. Molar thermodynamic properties of pure substance. You see, molar is for 1 mole of every substance. And they are standard. Look at the symbol for the standard here. And look, delta H standard of formation in kilojoules per mole. So when you get to one of these tables, you need to look. You need to read initially what type of table is that. See, it's molar, so yes, that's good because we are using a standard molar concentration. And that's what we need. Also look for the units. Units for delta H of formations are in general kilojoules per mole. These are standard free energies of formation. And we are going to talk about this later. And we have here the standard entropies. Remember, here we are using absolute values, whereas here and here we are using relative values that depends on the final and initial conditions. In this chapter, we are going to focus on these 3 columns. Here we have the heat capacities for the same substances. But we are not going to use this now. So we're going to use those 3. I'll show you later how to use this one, but it's going to work in similar manner. On this table, you need to look, when you're trying to find a substance, you need to find exactly the same substance you have on your chemical reaction. For instance, let's say in your reaction you are working with silver. Look, here you find 3 forms of silver. Silver C, that stands for crystal, that means solid. Silver gas, that's atomic gas. And silver plus ion, Ag plus gas. So your values will change depending on the state of your substance. Sorry about the alarm noise. All right. So yes, check for the states. So you need to make sure that you are taking the right magnitude, the right measurement for the substance that is in your chemical reaction. Also check for the units and make sure your data table, the one that you choose to use, is using the SI system units of energy. You may find, don't be surprised if you find some data tables, some thermodynamic data tables written in calories. You can use those, but you need to make the conversions to kilojoules if you need to use kilojoules. Some engineered data tables even gives you values in BTUs. In a British system. So double check that you have the right functions you need, the right units, and you choose the right state, the right phase of the substance. When I'm looking for these numbers, values of delta H and values of entropies, I like to compare 2 or 3 data tables. Just to double check, we're talking about the same number. Probably you won't find exactly the same number on 3 different data tables. Like for example, Hg gas in this data table is showing delta H standard of formation is 284.55 kilojoules per mole. If you compare that number to the one given in a different table, probably it's going to be, you will find a slight difference, like 283.94, for example. But that's not a big deal. You can use either one, but the 2 numbers are very close and you can take either one. At the end, your results will be within the same order of magnitude, and the error introduced is minor, and that's due to the precision of the experiments conducted and other factors. But you will see that the 2 numbers on 2 different tables are related, are close related. So probably they are close to the real true value. That is hard to define. But if you see 2 data, 2 numbers very different, so you have to be careful, you have to keep searching for those. You don't want to look for data tables. There's another, nowadays it's a lot easier because you go, let's say you want to know delta H and the entropy. Notice the entropy is absolute, there's no delta because we have absolutes. There's a way to measure absolute numbers for this. There's no way to measure absolute values for this. There are no physical ways to measure these absolute values. There are no physical ways to measure these absolute values. That's why we measure the changes. Compare between final and initial states. Another way to do it is sometimes I just go here. Let's say ammonia. I want to know these variables. I go here, look. I like to use this one because that gives you a very fair, good numbers. And then you go somewhere here and it gives you a lot of information. And let's say we're looking for delta H for ammonia. You go down Yes, the melting point, the boiling point, critical point, solubility in water, solubilities, standard molar entropy. This is the thermochemistry of that substance. 193 joules per mole. So the entropies are given in joules per mole Kelvin. Whereas enthalpies again are given in kilojoules per mole. So here the standard enthalpy of formation for ammonia is negative 46 kilojoules per mole. That's for the formation of just one mole of ammonia from its elements in their standard states. So that's another way to find these numbers. Once you have those numbers, write it down, put it on top of every substance in your chemical reaction. I'll show you how I like to do it to keep everything, your numbers organized. So let's do this one. So I went to my data table and I found these entropies in joules per Kelvin mole. 186 for CH4, sorry. 205 for O2 gas. 214 for CO2 gas. And 70 for water liquid. Remember, you need to match the state of your substance. So what I like to do, sometimes we need to do some calculations. I like to put the list on the bottom of the equation, or sometimes one on top and one on the bottom. Entropies and delta H. Many times we need to use both. So you will make a row here, another row. I like to put it separate. Probably the other one I will put on top of the equation. So here I will write delta H. So you find on the data table, find the delta H for this, for this, for this, and for this. And like now, we are going to use the entropy. So you put a row here, 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 and here. And then you can proceed to do your calculation. So let's calculate delta S. This is delta. Delta S equals, and we are going to use this one, the sum of n entropies of products. And I like, in order to prevent any confusion, any mistake with the signs, I like to use square brackets to separate my products and my reactives. You see? Reactive products minus reactives. That's final minus initial. And you need to make sure what are the signs of these values. Let me see if on my table I have one of those to show you. to prevent any mistake. Also notice we have some rules that standard enthalpies of formation of pure substances in their standard state is 0. Any pure substance, any element from the periodic table, pure, in their standard state has 0 enthalpy and 0 free energy. But they do have entropy. Some of them, no, a lot of them. But the first rule of beryllium is an element in its pure 0, 0. There's enthalpy and entropy. Sorry, free energy. So let's say CH4 methane as a gas, the entropy is 186. It's positive. You have to be careful with the signs of these values. You don't want to miss the sign. So and let's compare this table. This is 186.264 joules per Kelvin mole here. And this is joules per Kelvin mole, whereas this is kilojoules per mole. All right, I can go back to the problem. You see, there's a slight difference here, but it's fine with these values. Let's start solving it. So it's going to be the sum of n delta S. What is the meaning of n entropies? We don't need delta here. Delta is for the total change, but here we have absolute values of entropies. So we can really delete the n. Oh, no. N is good, but what we can delete is the delta. That's what I was talking about, right? But the n, of course, we need it because we need the stoichiometry of the equation. Products here. N, how many CO2s in the balance? You have to check, make sure the equation is balanced. How many? 1, right? So it's going to be 214 positive, 214. It's 1. And it's the sum. So we add all products and multiply every entropy by its stoichiometric coefficient. So plus for water, we have 2 times the entropy of water, which is 70. And that is for the products. Now, minus the sum of n standard entropies of reactives. So we have 1 CH4, that's 1 times 186, plus we have 2 oxygens there, but the oxygen has standard entropy of 205. And that's it. I normally don't write 1, just showing you here so you make the relationship there. So you do the addition subtraction and you should get negative 242 joules per Kelvin mole. So very important, to follow the signs here. I will double check this one. You can double check. Everyone, please do the calculation. Do the calculation and verify that you get the same answer. This reaction, according to this value, is telling you some information about the entropy. Remember that entropy gives you an idea of the tendency of the substances to gain entropy. Nature loves systems that gain entropy. The entropy here is negative, telling you that there's lower probability to get the products, as you have it written here. Because this reaction is actually decreasing the entropy. You see the entropy here is going down. So that you can say the delta H, sorry, not delta H, delta S for the reaction goes down. It's negative. And nature don't like that very much. Nature prefers to increase entropy, to increase the state of disorder. And let's see. Let's check the reaction. What's happening at the reaction level? On reactives, we have gases. Everything is a gas. Gases shows a lot of entropy because every molecule has more freedom to move, has more degrees of freedom in all directions. And they can perform several types of vibration. But when we compare to the products, look what happened. Two gases making a gas, this is good, nature likes that. And what about here? Liquid. Liquid, the liquid state, you have molecules in a better state of order, more organized than water gas. So that's why in this reaction producing water liquid, the entropy went down. So sometimes we can make predictions in terms of the direction of the reaction and the spontaneity of the reaction and the probabilities to make products. Just by looking the chemical reaction, you can find a lot of information. For gases, the entropy increases as volume increases. We have a gas in this volume and when we increase the volume and you open the door, what's happening naturally, spontaneously? Molecules will expand or diffuse, probably is better word here, diffuse into a higher volume, increasing more degrees of freedom. Now molecules have more freedom to move in a bigger volume. So it's clear here, the entropy here is bigger. So the entropy of these molecules went up. Entropy is positive here, and here the entropy is negative. more disordered, more organized. And you keep compressing these molecules, they can become liquid. So that means here, the entropy is even more negative. Entropy goes down. If you keep compressing this substance, you can even get solid crystals. Now molecules have much, much less freedom, less and less freedom, I should say. Molecules or particles will have less and less and less freedom to move. Therefore, the entropy is very low. The number is going to be even more negative. So in a chemical reaction, as a conclusion, chemical reaction that increases volume has more entropy. But the chemical reaction that produces gases has more entropy than the one that produces liquid, and that one has more entropy than the ones that produce solids. If temperature increases, entropy increases. Makes sense because this is the solid, this is the liquid state, and this represents the gas. Increasing temperature means increasing kinetic energy, and particles goes to gas phase, where they have more freedom. The physical state. Entropy increases when the substance goes from solid to liquid, from liquid to gas. So those are the hints that can help you to make predictions on the spontaneity and changes of entropy for a chemical reaction. In general, if delta N of gas, the change of gas, increases, then the change of entropy becomes positive. And that is good in terms of what nature likes. So that means there's more probability that the process will occur. If the change of gases during the reaction decreases, then the entropy decreases, becomes negative, and there's less chance for the reaction to occur. In terms of number of particles, number of moles, when we increase the number of particles, there's a tendency to increase entropy. Increasing number of particles, if the reaction is making more particles, that means the reaction is increasing the entropy, increasing the state of disorder of the system. Now you have more things to organize. So let's see here. Let's make predictions in the real chemical reactions. I'm going to do a couple of them. I'll show you what type of analysis we need to do to make these predictions. We need to predict if the reaction will increase entropy or decrease entropy based on what we just learned. Let's check this reaction. What will happen with delta S, the standard of the reaction? We don't even need to calculate it. We're just making predictions. That's the part we are working here. Without making actual number calculations, we do the analysis, critical thinking to predict. And once you do the calculation, you should arrive to the same prediction you did. Let's compare what we have on each side of the equation. Products and reactives. So on the reactives, we have a solid, we have a gas, and we have a gas. How many gas particles? We have 1 and 1. We know solids have low entropy. Gases have high entropy. Let's see on the product side, what do we have? Solid. So all these are reacting together to make a solid. What do you think? Does nature loves to do that spontaneously? The reaction is no. This reaction, we are predicting that this reaction will have what sign of entropy, negative. We are not making predictions in terms of the magnitude. In order to find the magnitude, we need to find the values, as I showed you before in the data table, put it there, replace, and find delta S using the formula. No, not this time. We are just making predictions in terms of the sign. The tendency will decrease. Will the reaction decrease entropies on the products, or will increase the entropy on the products? Second one. Here, all species are in gas phase. So what factor, what else we can use to find if the entropy will increase or decrease? Number of particles, right? We know that nature will increase entropy if there's more particles. Here, this is balanced. We have one molecule, one particle here. So 2 particles reacting, and as a result of the reaction, it will produce how many particles? 4. That will increase the entropy. So you say the entropy of this is going to be positive. And so on and so forth. So you do that type of analysis on everyone. So I'll let you do this, do the same type of analysis, and then you can post your results on that discussion board. And you can give your inputs about your partner's responses. So the second law of thermodynamics, as a summary, says that the entropy of the universe is increasing. That's what we talk about. One of the theories is the expansion of the universe, proved by the shifting of red, the Doppler effect. And as we can summarize that the total change of entropy of the system equals the change of entropy of the system plus the change of entropy of surroundings. One way to measure the entropy is taking the heat of the system, measured at a constant pressure over absolute temperature of your reaction. So you know the delta H of the system for a negative process, for exothermic processes, divided by temperature will give you the delta S of surroundings. So the total entropy of the system equals the change of entropy of the system minus delta H of the system over temperature. From here, we found that T delta S total of the system equals delta H of the system minus T delta S of the system. This conclusion brings us to another concept in thermochemistry. For a natural process, minus T delta S total of the system is called the free energy. Free gives energy. So for a natural process to occur, or process to occur naturally, the free energy or Gibbs free energy has to be negative. So we can use G, stands for Gibbs free energy. Gibbs was a physical chemist that worked hard on these concepts. Free energy is just a concept of the energy of the system. Doesn't mean it's free. The definition of energy will help us to identify spontaneous processes. Remember, for any spontaneous process, delta G must be negative, according with the previous concept here. Negative T delta S total of the system, and this is the definition of free energy. So we label this T delta S total as free energy, delta G, the change of free energy, which is equals to delta H of the system minus T delta S of the system. And again, has to be negative for a spontaneous process. If you calculate delta G for any reaction, and that reaction, and that number, that calculation gives you a positive number, that means your reaction will not be spontaneous. Since we're talking about a state function, delta G is a state function, so that means we can measure final states and initial states and find the gradient, the change for that function. So there are two ways to measure it. Measuring the final free energies, that means the products minus free energies initial means reactives. So that's one way that we can measure it the way I showed you before. So delta G, standard of the reaction, is going to be the sum of N delta G standard of formation of products minus the sum of N delta G standard of formation of reactives. So that is this, final minus initial. So that's one way to measure delta. The other way to measure delta G is just using this relationship. Delta G equals delta H minus T delta S at constant temperature or pressure. So if we use standard conditions, we have delta G standard equals delta H standard minus T delta S standard. Most of the times we don't have a standard temperature, but that will affect very little on the changes of delta H and entropies. So in general, we can say that delta G of the reaction equals delta H minus T delta S. And we use all these standard values given on the data table, and you can use the temperature given on your problem. And use data table to find delta H of the reaction. As I showed you before, use the data table to find delta S of the reaction and plug these numbers here to find delta G of the reaction. Since most of the times on the problems will ask you find, they give you a reaction A plus B to form C and D. The problem will ask you find delta H of the reaction. How do you find delta H of the reaction? You know, sum of N delta H standard of formation of products minus the sum of N delta H standard of formation of reactives. So you do that. Use the data table to find those. What data table? The thermodynamic data table. And then the problem asks you find delta S for that reaction. How do you find delta S for the reaction? Same thing. You go to the data table, take the entropies of every reactive and every product and apply into similar formula. The sum of N standard entropies of the products minus the sum of N entropies standard of reactives. And then usually the problem also will ask you find what is delta G for the reaction. So how do you find delta G? You have two ways. You can do it using delta G of the reaction equals delta H of the reaction minus T delta S of the reaction. Since you already took these measurements, so you plug this number over here, plug that number over here, temperature is given, and solve it. Be careful with the signs. Signs are very important. Now, if you have plenty of time, you can find delta G this way. This way. And then the problem will ask you, is that reaction spontaneous? Is that reaction spontaneous? That reaction A plus B forming C and D, is that going to be spontaneous or not? To answer that, just look. You just found delta G. Look for that sign. If delta G of that reaction becomes negative, so you say, yes, the reaction is spontaneous. Because delta G is negative. If the delta G becomes positive after you do this calculation, so your answer here is no, because delta G is positive. So you see, when we find delta G, we really don't care on the magnitude. How big is that number or how small is that number? We don't care. We don't need it now to do the prediction. In order to do the prediction, what we need to know is the sign. For all spontaneous processes, delta G must be negative. And delta G basically measures what gives us, but that number is to measure the actual work done, useful work done by the system. So you are more interested on the sign to make the predictions. What about if delta G equals 0? That's possible. It's not negative, it's not positive, but you find delta G equals 0. What would you say? Since delta G measures the useful work done by the system, and delta G becomes 0, that means the system is not doing work. The system is not doing work. If the system is not doing work, give me possibilities. What's going on with the system? A plus B to form C and D, and it's not doing work. Net work. You should write that. Net work. It's like the system stopped doing work. When delta G is positive, the system is doing positive work. When delta G is negative, the system is actually doing work on surroundings. When delta G is positive, the system is not doing work. It's not producing any net work. So the energy is not being converted into work. The energy is being converted into heat, but no work, no useful work. If delta G becomes zero, the system is not doing work at all. When does happen? What is the key word there? What do you say? Yes. Again, equilibrium. The system is at equilibrium. It's a dynamic equilibrium. The speed of the forward reaction equals the speed of the reverse reaction. Delta G equals zero. The system is not doing useful work. And we can make modifications, changes on thermodynamic conditions, increasing delta H, decreasing delta H, increasing temperature, increasing or lowering temperature, in order to make the system to work. And how do you make the system to work? You need to make delta G less than zero. Delta G must be negative. So I'll show you how to figure those conditions. So here I like this table because this one shows you how to make predictions in terms of spontaneity of the chemical reaction. So we have several possibilities here. Let's analyze the free energy equation. The free energy equation says that delta G of the system equals delta H of the system minus T delta S of the system. This is our fantastic equation that will help us to make predictions in terms of spontaneity of the reaction. This will let you know if the reaction is going to work or not under given thermodynamic conditions. So let's see, we have different possibilities depending basically on the signs of delta H and delta S. Those possibilities are if delta H is positive and delta S is positive, will the reaction produce work? Is the reaction going to be spontaneous? Remember, we are looking for any combination here to achieve a negative delta G. In any case, to be spontaneous, delta G must be negative. So basically what we're trying to find here is the sign of delta G. But the sign, in this case negative, because that's what we're looking for a spontaneous process. The sign of delta G will depend on the sign of these two variables. And also on the temperature. So that's why we are doing different combination of signs here, because some reactions can be positive, can have delta H positive and delta S positive. Not the magnitude. Here we are not interested in knowing how big is the number of delta S, only the sign. So if delta H for that reaction is positive and delta S you found to be also positive, what are the chances using these combinations here? Remember, this is negative, and affecting the negative is affecting everything here. So you have positive, you need to do sign operations. You remember the sign of operating signs? Like the friend of my friend is my friend, right? Plus equals plus. When you are doing addition or subtraction of signs. What about the friend of my enemy? Plus minus. The friend of your enemy is your enemy. What about the enemy of my friend? The enemy of my friend is my friend. What about the enemy of my enemy? The enemy of my enemy is my friend. Yes? Oh. So basically you follow these rules of addition, subtraction of signs. But here, these numbers here will depend on the values. Some of those will depend on the values you have. But let's analyze here. Remember, we have a negative sign here affecting everything here. So you have plus, this minus, change the sign of this. Plus and minus. So plus or minus, what will you get? You get plus or minus, right? Or minus, depending on what. If you have plus and plus minus here, how did you get this negative or positive? So let's analyze. Plus minus plus, which is negative. What do you get here? Remember, we're looking for minus. Is a chance that this term here becomes negative? Well, depends on the value of this, right? No, this, because this is positive anyway, and this is the sign for delta H. But here we have temperature. Temperature can change this. Because if this number becomes very large, larger than this, the whole thing will become negative. So temperature makes up a big factor here. If temperature is big enough, the whole thing will become negative. If temperature is low, therefore this number will be lower, bigger than this, big positive number minus a small negative number gives you positive. And we don't want that. We are looking for the negative. So that has to be big number multiplying here. So everything will have a big negative number plus a small positive number it becomes negative. For example, let me give you real numbers so you don't get confused. Let's say how 4 minus, this is positive, minus 8. Okay, minus 9. What is the result? Minus 5. But what about, so this number, in order to be negative, this number has to be bigger than that. This number is not changing here. 4 minus 3. How much is that? 4 minus 3 is plus 1. So you see, if we have a small number here, the whole thing will become positive and will be not spontaneous. If we have a big number on this term, the result will be negative and the system or the reaction or the process will be spontaneous. But who can make this number bigger or smaller? This temperature. If temperature is low, this number will become smaller at some point, and the whole thing will become positive, non-spontaneous. If this temperature is high, this term will become higher than this eventually, and everything will be negative for a spontaneous process. So we say when delta H is positive and delta H is positive and delta S is positive, it will be spontaneous only at high temperature. When T delta S becomes bigger than delta H. So this has to be bigger than this in order to become negative. Only. So plus and plus depends on temperature, at high temperatures. You need to find a way to remember that. When you see plus and plus for the delta, you measure the delta H of the reaction. How? I showed you before. Yeah. I'll give you a problem, reaction. I'll give you the data table. You find the values, find delta H for that reaction. Then you find delta S for that reaction. And then you find delta G. And you will find if delta G is negative, positive. But even before you get this, and if you know all these two, delta H and delta S, and know the temperature, you can make the prediction without doing the calculation. And this is how you do it. So, next situation. What about if delta H is positive and delta S is negative? Oh, before I go to this, let's do one more analysis. Does nature loves to do endothermic processes? Not that much, right? Because those systems will gain more potential energy. So nature don't like that much this portion being positive. What about, does nature likes to have more entropy? Yes. So nature loves, don't like that, nature loves that, and everything will depend upon temperature only. Second case, delta H is positive, that will be an endothermic process, nature don't like that. It's not attracted to do that. What about delta S? Means what? Negative. The system is gaining order. Does nature loves that, loves to do that? Not really. So here we have a situation with two processes happening that nature don't like that much, making endothermic reactions to gain more potential energy and making more organized systems, less entropy. Any combination of this is going to be always positive because negative times negative is positive. Negative times negative is positive. Positive and positive is positive. So delta G here, delta G will be positive. Here delta G depends only will be negative only at high temperatures. And here, this combination will always give you positive delta G, that means never spontaneous. So when you see a reaction, when delta H of the reaction is positive, delta S of the reaction is negative, you know that reaction will not occur. No matter what you do with that reaction will not occur, will not happen on this part of the universe. What about the next combination? Negative, positive. What is this negative delta H? That means exothermic. Does nature loves exothermic reaction? Yes. It loves it because it reduces the potential energy of the system. Does nature loves positive entropies? Yes, because it increases the state of disorder. So what about the combination of signs here? This is negative times positive equals negative, right? Negative times positive equals positive. Oh, so negative times positive equals negative. So, and negative plus negative, always negative. So this is negative, and this is negative. This is going to be delta H. Delta G is going to be always negative. Means what? Always. Spontaneous. This one, never. Spontaneous. This one, always. Spontaneous. Yes, because nature loves exothermic and loves to have more organized, more disorder. What about the next case? When we have negative and negative. Nature loves this exothermic reaction. Nature don't like this much because that negative delta S means more organized. So nature don't like that. Now, what about the combination of signs? Negative times negative equals positive. Positive plus minus, it depends, right? It could be positive or negative, similar to the situation we had before. But this time we are switching the signs. Let's analyze. So this is going to be negative, right? So we have, let's say, -4. Let's use the same numbers we have here. Negative, and this is going to be negative. So negative 4 minus 9. How much is this? This is going to be, you add, it's going to be 13. Let's see the other possibility. This number is fixed because we only have delta H here. So this one will change the magnitude depending on temperature. What about if we have negative four minus negative 3? It's going to be 7. So the value, this value will depend again on temperature. The temperature can make this bigger or smaller. If this number becomes bigger than this, then it's going to be positive, delta G. If this number becomes lower than delta H, then everything will become negative. So it will be spontaneous only at, will be negative only at lower temperatures. So that will help you, will help us to make predictions on the spontaneity of the reaction. Here is the summary again. It's another version of the same table, same analysis. Here is one example. We're going to use this example to apply all these concepts. I'm going to leave it here. I continue on the next chapter. I don't want to make those videos too long. All right, so see you on the next part.